generalized theory of ferromagnetism. So when you look at any magnetic material, so in experiments, so what was observed? So when you measure the magnetization as a function of field, so you observe that, let's say this is your iron, this is cobalt, and this is nickel. So what you observe is different materials have different saturation magnetization, and also the shape of the curve is also different. Which one is getting saturated faster, and how it is getting saturated? Everything is different for different materials, and so there was no explanation like in 1900. So when these experiments were done, and Weiss he gave a theory which is still quite relevant. So first thing what he said is like most likely there are a lot of magnetic moments. So we have many magnetic moments, and in these particular materials, in ferromagnetic materials, so they orient or get a spontaneous polarization. And this spontaneous polarization is proportional to, or this magnetization is proportional to your molecular field Hm. So this is called as molecular field, or sometimes also known as mean field. And this is the coefficient. So that means these particular materials have some kind of molecular field or some internal field which is quite large and makes sure, which is still present without any magnetic field, any external magnetic field. And this is, let's say, an internal field. And that makes sure that these moments are aligned along a particular direction and gives rise to a spontaneous polarization. But now if you take a piece of iron, it is typically not magnetic, right? Only when you bring it very close to a magnet and then you can magnetize it, okay? So how do you explain that? So to explain that, he said these materials are not made of, like, all the magnetic moments are not aligned like this. Rather, they are made up of domains. Okay. So you have a material, and you might have one domain. So this is like you have only one single domain. Instead of having a single domain, you have multiple domains. Where the magnetic moments are in one domain, they are all aligned in one direction, in a particular direction. But when you look at the macroscopic picture, so they all cancel each other out. So in this case, M will be equal to 0. So what happens in the process of this magnetization? So this is a process of magnetization. So you have basically zero magnetization, or that means this domain, multi-domain system. So you can take an example. So let's say you have two domains. Okay. So here M is equal to 0. Now you apply a magnetic field in this direction. So what happens is, so due to the field, so these lines are called, so these are the domains, okay? So this is your domain, and these lines which separate the domains are called domain walls. Okay, so these are the domain walls. Now, when a magnetic field is applied, so the preferred orientation now is this direction. So this domain wall moves down. So you will have the domain wall somewhere here, and this domain grows. So the upper domain grows relative to the lower domain. And then when you apply even stronger field, so what happens is, again, wrong. So if you apply a stronger field, so this is your domain wall now, and this domain, the upper domain grows and the bottom domain shrinks. Basically, the domain wall moves, and finally at saturation, so you will have a single domain. Finally, you will have a single domain where the saturation, the spontaneous polarization of the saturation happens. So this is like just two postulates he postulated. It is not like verified at that time, but they are so profound. I mean, still they are true actually. These two, his assumptions are postulates. So one is that you have spontaneous polarization due to this molecular field. So all the atomic moments inside the domain, they feel the same molecular field, and they try to orient along the same direction. And the second is the material is made up of domains and domain walls. So these are the two postulates which were quite profound at that time and still kind of led to all the development in magnetism. So from this expression, in fact, we can actually derive the Curie-Weiss law. So what we saw in the previous class, that you can derive Curie law using this Langevin function, but here we can derive using this molecular field, we can derive the Curie-Weiss law. Okay, so let's do that. So if I have, so I say my molecular field M, the magnetization is, oh sorry, I did a mistake in the previous one. So it should be the other way around. So we should write the molecular field Hm is gamma into M. So not the other way around. Okay, so this is your molecular field. Okay. So M is your magnetization. And when we say, so if you go back to the Curie law or the Langevin function, so what you have is M or susceptibility is n mu square by 3 kV t, right? So this is your susceptibility from the, so if you use the function and assume that your A is much smaller than 1. This is what you get the susceptibility. So you can write down that M, so this is chi is basically your M by H. So it is n mu square H by 3 kV t. So now you say here the magnetization is due to the molecular field. So according to Weiss, so we can say this is Hm by 3 kBT. Okay. Or in fact, we don't say. So we have this is your applied field, external field. So in addition to that, you have this molecular field. So we can say we have H plus Hm. This is now the field which is true for a ferromagnetic material. So remember, this molecular field is always there. Doesn't matter what is the temperature. So whether you are below QE temperature or above it, so molecular field is always present. So in place of this Hm, so you can now substitute as H by 3 kBT plus mu square by 3 kBT to gamma m. Now you can bring this to the left hand side. So you will have 1 minus n mu square by 3 kBT gamma m equal to n mu square h by 3 kBT. So we can calculate susceptibility now. So I think this is visible. So let's say I can put this here. So m will be, or susceptibility is m by h, which will be equal to n mu square by 3 kBT divided by 1 minus n mu square by 3 kBT gamma. So you can do a simplification, and what we will get is so if you simplify it, so you get something like T minus T. So I write down this T minus Tc. So this is your Curie Weiss law. And Tc will be how much? Tc will be equal to n mu square gamma by 3 kb, or you can write down this gamma c. So this is how you can write down. So this is your Tc, your Curie temperature. Okay. So this is your Curie Weiss law. You can get just using a simple assumption that all the magnetic moments are experiencing a molecular field. So you get this. So now if I want to so expand, let's say, this understanding a little bit. So we can understand it from a graphical point of view. So let's say we start with so if you plot chi versus t, so we already did that. So this is something like this. This is Curie law, and this will be your Curie Weiss law. Yes. So this is as a function of temperature. Yes.
Can you make the diagram on the little bit more right side? Your board is not visible.
Not visible?
Not.
So I make it here on this side?
Yes, sir.
Okay. So what I plot here is chi versus t. So according to Curie law, it will be like this. This is and if you take Y's law, is something like this. So this is your TC. Okay. So now if we uh, like try to understand it in a better way. So just a moment. Okay. So in 5 minutes, yeah. So we can write down. So from the Lagrange's function, we know that m by m0 is equal to Lagrange's function. So where it is got hyperbolic a minus 1 by a, and where a is equal to mu h by kb. So if we say we have, let's say we don't have any magnetic field, external magnetic field, so we can write it as mu h m by kbt. So when h is equal to 0, this is an external field, it is 0. And in that case, we can write down, so again A will be equal to mu gamma m by kbt, and we can write down as m, this as m, a little bit of reshuffling, so I'm doing. So I can write down m by m0 as kbt by mu gamma a by m0. I can write down like that, or I can write down it mu gamma m0 into a. So I have one equation, something, let's say equation 1 and equation 2. Okay, and we will plot it. So if you plot both the equations simultaneously, so this is your, so you plot m versus hm, and this is your at a particular temperature T. So this is how it looks like. Yeah, this is not hyperbolic. Okay, so this is how the plot. So equation 1 is a straight line, or rather I would plot, yeah, so as a function of, so this is m by m0 as a function of a. So this is a straight line, and this is your Lagrange function. Okay, so we'll, because we need some more time to discuss on this, and it is already